Aldrin Urbi and Marian Miranda. And again, reminders to the speakers.
Sorry.
Sorry.
Pinag-uusapan lang kami dito. But if the speakers are here, we can begin.
Yes,
Were the speakers here? Rain?
Yes po, they're all here po, ma'am.
Hello?
Sige, go Jan.
Hello, can you hear me?
Yes, clear siya.
Okay. Okay, good afternoon, VIP and Optical. I am Janoa Gamala, and I will be your moderator for today's session. So again, our speakers for today are Aldrin Urbi and Marian Miranda. And reminders to the speakers, you have 12 minutes for your presentation and 3 minutes for your question and answer. So we may now begin with the first speaker. Aldrin, are you ready?
Yes. Am I audible?
Yes, you are.
Okay. I'll just share my screen. Is my screen seen?
Yes, we can see your screen.
Yes.
So I'll start now. Good afternoon, VIP. I am Aldrin Urbi, and I will be presenting this paper entitled Single Pixel 3D Imaging with Phase Shifting Fringe Projection from the journal Optics and Lasers in Engineering with an impact factor of 4.836. Fringe pattern profilometry has become the most widely used 3D imaging due to its flexibility and high accuracy. For those unfamiliar with fringe pattern profilometry, it is a 3D image reconstruction technique which makes use of different fringe patterns of different faces. So they project these fringe patterns onto an object, and then a camera normally captures a picture of the object. So essentially they have 4 different images with different fringe patterns, and then these different images would be used to reconstruct the object. And then single pixel imaging, or SPI, can obtain computationally correlation imaging using a single pixel detector without spatial resolution. It is mentioned in the paper that single pixel imaging has the potential of 3D imaging by simply combining it with traditional 3D imaging techniques. So they propose to use fringe pattern profilometry for single pixel imaging because phase shifting usually provides better stability and accuracy for phase retrievals regardless of surface texture. So this is their proposed setup. So they have essentially integrated a fringe pattern profilometry setup with a single pixel imaging setup into one. So we have here they have the first DMD, which projects the fringe patterns to the reference plane along with the object. And then we have a second DMD here. So we have a camera lens. This camera will capture the image with the fringe projection, and then it will project that into the second DMD, which is displaying a Hadamard matrix. So they're essentially making use of Hadamard single pixel imaging, which is a method of single pixel imaging using essentially the Hadamard matrix. And then we have the single point detector pointed here in the second DMD. This will capture, so it will capture the single point detector will be the one getting the measurements from the DMD, and then it will go onto the computer. And the image on the right, we have the DMD. So it's projecting the fringe patterns here, as stated earlier. And then you can see here in this part, so they have the they have a hemisphere here with fringe pattern projections. As you can see, the fringe patterns distort. So since they distort, so you can see these distortions that this can be used to um reconstruct the image in with with the height. So yeah, so it has a definite volume. So this is their system framework. So as I've said earlier, they have fringe patterns. They project it onto the image or onto the object. The fringe image is then acquired by the SPI subsystem, or so the face information, which contains the shape of the object, is retrieved, and then the 3D shape of the object can be calculated using the retrieved face. So this is again an overview or an overhead view of their setup. So they have the two DMDs. They project. So they have the reference plane here, and then yes. So they will be making use of parallel projection. And then this is the equation that they will be used for the phase to height conversions as well as global phase XY conversions. This is so that the actual measurements of the subject or the object is consistent with the measurements of the reconstructed image. For the single pixel imaging part, as I've said earlier, they will be using Hadamard matrices to create the modulation patterns. A is the Hadamard matrix in the equations here. So as you can see, we have this Hadamard pattern A multiplied to the image, which will result into Y. So to reconstruct the image, all we have to do is to get the inverse of the Hadamard matrix, or the inverse of the Hadamard matrix, and multiply it to the resulting image Y to get the original image X. In this case, they will be ignoring the background noise, and the reconstruction of the image is done using equation 5. And then, so the phase retrieval, they will be using the classical 4-step phase shifting algorithm for phase calculation. So they didn't they didn't put the equation that they will be using in the paper, but I assume that it is similar to the other other papers which make use of the 4-step phase shifting algorithm. In this case, since it's a 4-step phase shifting, it's in multiples of pi/2. The spatial phase unwrapping algorithm is employed to generate the unwrap phase, and then the phase wrap is in the range of -pi to pi, a complete circle essentially. And then this is their experimental setup. And as I mentioned earlier, we have the DMDs, and then the projection. They will project the fringe image into this plane, and then they have the camera and the DMD that will be displaying the Hadamard matrices. Then they have the single point detector connected to their computer, which will then stitch the images together. And then they also have the displacement platform with the stepper motor, so they can move their reference plane essentially. So for the experiment and results, so reconstruction resolution is limited to 128 by 128 pixels. It is because anything beyond 128 by 128 pixels, for generating Hadamard matrices for anything more than 128 by 128 pixel image would result in a very long process a very long process. And then the absolute phase retrieval includes 4 fringe images and a stripe image. So the total number of detections would be 5 times 128 times 128. So this is the total number of pixels that they will measure just for one reconstruction of a 3D image. So they tried it on a quarter ball with a radius of 25 millimeters. So they tested it on a quarter ball since it is easy to reconstruct and therefore easy to the comparison between the experimental and the simulated quarter ball is simpler. So it's simpler to get the error. So as you can see here, they have the 4 different fringe patterns. So these are all different. As you can see here, it's the fringes are moving. And then this is the actual object. This is the reconstruction at D. So as you can see, it sort of captures the sphere, but the quarter ball, but it has so it's not that perfect. So they measured an RMSE value of 0.158 millimeters. They argued that since the error is submillimetric, it is acceptable since submillimetric error is acceptable for many 3D imaging applications. They also tried it on more complex objects. So they tried it
Excuse
here.
me, you have 2 minutes left.
Okay, thank you. So they tried it on more complex objects, which is the pyramid and then the ladybug. So as you can see here, they have the pyramid and the ladybug. So they did what they did earlier with the quarter ball. They projected fringe patterns onto it, and then they reconstructed it. Since they noted already that their error is small, we can assume that the measurements gathered or the measurements of this reconstruction here is accurate to that of the actual measurements of the object. So as you can see here, it has a height of 14 millimeters, and then while the ladybug has a height of 15 millimeters. And then they were able to reconstruct the general shape of the object. They even captured the small protrusions on the back of the ladybug, although it's not really that distinct, or it's not really that noticeable, but at the very least it shows under a 3D reconstruction. And then finally, for their conclusion, the proposed method is successful in the reconstruction of a sphere or a quarter ball with a radius of 25 millimeters, as well as the reconstruction of a ladybug and a pyramid. So their errors seem to have come from technical issues from their experimental setup, as well as their calibration. They said that their calibrations were very simple, so it caused a bit of an error on their reconstruction. And then they noted that their measurement error is much larger than that of a conventional FPP, which is predictable, since instead of using an actual camera, they use a single pixel detector instead. So that's it for my presentation.
Thank you so much, and we're now opening the floor to questions.
May I ask a question?
Yes, ma'am, go ahead.
Why do they need a Hadamard Hadamard matrix? Why can't they just use the actual patterns for modulation?
Ma'am, it's because it's been proven in other papers that using Hadamard matrices is more efficient when it comes to single pixel imaging. So I think that's why they use Hadamard. Yeah.
In what sense efficient?
It has, so using a Hadamard matrix for single pixel imaging will typically result to a better quality of reconstruction. In usually this is measured using the PSNR or SSIM, and then it also has a shorter process, or has a shorter, it has a shorter time to do for it's shorter than the typical single pixel imaging. Yun po, ma'am. It's essentially shorter time and better reconstruction quality.
I have other questions, but I'll let the others ask first.
Okay, so our second question will be coming from Sir Rene.
Hello. My question is, based on your error conclusion, I think they were all systematic errors, but do you think there's a random factor here, random errors, and could it be solved by using repeated trials? I mean, this is a physics 191 question. In short, are the errors purely systematic, or are there random errors present in these types of experiments, and could they be reduced using repeated trials?
Yes, I think so. That repeated trials can reduce some of the error, but especially when it comes to technical issues, since in an actual experimentation setup, especially for fringe pattern profilometry, I think it's best to have multiple trials, since there is always a possibility of human error in when it comes to the whole process of doing it.
I see. Follow-up question. So in the paper, they mentioned that they only did. How many trials did they do in the paper?
Oh, they didn't indicate the number of trials that they
Okay.
did in the paper.
Thank you.
I think we have no more time for another question, but if you do have more, you may send it in the chat box, or you may bring it up later if we have more time. So for our next speaker, we have Marian Miranda. Mar, you may start whenever you're ready.
Before I present, pwede may add lang po ako yung sa question po ni Ma'am uh, kay Aldrin, since same po kami na currently inaaral po namin yung Hadamard. So basically, tama po ba Ma'am na basically it does become faster for the reason na it is linear in terms of its process compared to other methods, and yung the mask used or the sampling techniques include patterns that are discrete in nature. So basically, those are reasons to make Hadamard faster compared to other techniques.
Wait, which ma'am are you talking to? Ma'am Chris Ritz or me?
Yung sa inyo po, ma'am, bali, curious lang din po ako, ma'am, na sa why Hadamard can be faster than other methods po. Like, dahil po ba mainly sa yung linear behavior niya po ba and discrete na patterns?
I actually not sure. I would like to have a look at the paper. Excuse me.
Okay po, ma'am. Thanks.
Hello. If I may interject, hello, ma'am. Can you hear me?
Yeah.
Yes. Okay. Okay, I think Hadamard patterns are basically faster for, say, fringe projection profilometry or single pixel imaging, because they only have binary values, black and white, whereas for say sinusoidal patterns, the typical ones used for in the DFT to the DFT, the patterns have, say, 256 values, so grayscale compared to binary. That's why Hadamard is much faster.
Actually, my question is why phase shifted tapos modulated pa by Hadamard? The phase shifted fringes are themselves grayscale. We can discuss later. Let's just have the next speaker finish first. Then, if there is spare time after, then we can discuss further.
All right. All right, Mar, you may start to share your screen.
Okay, I'll just share my screen. Kita ba ang slides?
Yes, we can see your slides.
So good afternoon, everyone. So I'll be presenting efficient ordering of the Hadamard basis for single pixel imaging by Lourdes Lopez Garcia et al. So all authors based in Mexico. So the paper is from the Optics Express Open Access Journal. This paper is published this year, April 8th. The journal is with an impact factor of 4.379 in the year 2020. So for the introduction, so single pixel imaging, or SPI, is known to reconstruct image by projecting series of spatial patterns on the target object and capturing the reflected light by a single photodetector or bucket detector. And one of the techniques assisting the single pixel imaging is the Hadamard technique. So particular in Hadamard pattern-based method, this is known to reconstruct an image perfectly, but sometimes it takes a long time computationally. So this is a problem in real-time applications with time constraints. So for this, for the paper, the authors propose an efficient method in ordering Hadamard basis patterns. So what they propose is said to have a computation complexity of n squared. So this is good since some of the ordering methods like the cake cutting or CC method has a complexity of n to the power 4. And for the proposal, so it consists of 2 steps. So the first step is simply to construct a 2D Hadamard basis patterns of dimensions 2 to the n from an initial sub-Hadamard matrices of dimensions 2 to the power of n over 2. Then this is followed by the second step, which is the zigzag traversal of the 2D pattern in step 1. So I'll show this. I'll show more detail of this later. So for the theory and methods, the Hadamard single pixel imaging is a linear in process and can be modeled with this equation 1 here, which is m equals pf, where f is the desired image to be reconstructed. The P is simply the Hadamard matrix with the patterns, and M is the corresponding measurements by the detectors. So in this system, we are trying to solve for F with the process called restoration. So for the experimental setup, we have here in the image the input image with containing the, or what shall we say, our target image labeled O, and illuminated by white LED diode, and some of the light will be reflected to a DMD or digital micromirroring device, which filters light and creates patterns, and some of this will again be reflected to the bucket detector, which is here in the image is the PD or the photo detector. Then going back to our equation 1, since we are solving for F, we can present it as equation 2, where F is equivalent to 1 over n h sub n multiplied by m, where m is a vector with all m sub j measurements, and hn is defined as or is equivalent to h plus minus h minus. So basically, hn is the Hadamard pattern, which is split into h plus and h minus. Simply put it as 2 patterns that are one that is the inverse of the other. So this is applied to the target image and help in reconstructing the image. So for generating the Hadamard pattern, patterns. So here in figure 2, the author started with a seed vector equivalent to 1, and then they try to manipulate this with 1D basis vectors, and until they finally get the sub matrices containing the Hadamard patterns here. So for the proposed ordering, so again, the zigzag traversal is shown here in image A. So this is how they will traverse the Hadamard pattern. So they will start in the upper left, since in the using the Hadamard technique, it is known that most of the energy is accumulated in the upper left. So this is where they will start and traverse it like this. So here in the middle image, the upper part is the GCS plus S ordering method, which is the proposed method, which stands for gray code sequence for the indexing plus S for sequencing for the ordering. So in comparison with the cake cutting method below, since it is also a good one, so we can compare it. And cake cutting is also another method where it differs in ordering, since it prioritizes the most significant pattern first, then ends with the least significant pattern. For the proposed method, the ordering prioritizes the computational part of the reconstruction of image. So that's why it has a somehow different ordering of the Hadamard patterns. So for the proposed method, it is called GCS plus S. So the GCS is gray code sequence. So they simply apply gray code technique in the indexing part. So gray code is like binary code, but computationally it is more efficient, since it only flips 1 digit at a time as we increase the value, unlike the binary counting where it sometimes flips 2 digits at a time as we increase the value. So computationally, the gray code is much better. So for the results and discussions, we have the simulations first. So here in the group of images, the last row is the proposed method beside the original image. So we can see that it competes with other methods such as the Walsh-Bailey and other ordering methods under the Hadamard technique. So we can see here that they are measured based on the RMSE and SSIM. And we can see that the proposed method in the last row is somehow doing better compared to other methods. Here in figure 5, they just use more samples. They get the images from the COCO database. They choose random images from it and also score them with RMSE and SSIM. So here in the plot, we can see that the purple line, which is the proposed method, is still competing with the other methods with varying sampling ratio in terms of RMSE and SSIM. And here in figure 6, similar with figure 5, but with Gaussian noise. So we can see a similar trend. For the experimental results, they use a 128 by 128 pixels for the images. And for this one, we can see qualitatively that the proposed method here in the rightmost column is still same with the simulation results, that is competing with the other methods. Numerically, here is the result. So we can see that the proposed method is still doing better than some of the methods, especially in the SSIM measures. So for this part, if you can say that somehow the proposed method is as good as CC, so in what way can we still check it if it can be a much more better technique? So the authors also tried to check the running time. So since CC is the one closest to the performance of the proposed method. So they compare them, and in terms of the running time with increasing dimension. So we can see here the red line is the proposed method that as we increase the dimension, it is with lesser running time compared to the CC, the blue line, even though they have almost the same image quality in terms of reconstruction. So for the conclusions, the proposed GCS plus S method is competitive with current methods in terms of image quality reconstruction. So this is limited to only the ordering method under the Hadamard technique. And additionally, the GCS plus S method gives a better computational complexity of n squared. This is important since the Hadamard basis complexity in terms of building and sorting grows exponentially with increasing dimensions. So that ends my presentation. Thank you.
We have a lot of time for questions, so if anyone has, you may share them.
Hello.
Yes, Ma'am Jean.
Thank you. Now it's becoming clear what the Hadamard transform's role is in in this technique. The Hadamard transform is the binary equivalent of the discrete cosine transform. It's like you binarize the discrete cosine transform, and the fact that you use the zigzag of the ordering of the Hadamard matrix or the coefficients of the Hadamard matrix or the projections of the Hadamard matrix is reminiscent of how JPEG or MPEG is discretized. So it's now clear. Thank you.
Do we have other questions for Mar? If there are, yes, Ma'am Jean.
So the only drawback perhaps I can think of is the fact that you would need an SLM to get this right, because unlike the usual technique where you just collect the light using a single pixel detector, this you have to have the light from the reflected up from the object to reflect or go through spatial light modulator, right? But the role of the spatial light modulator is that by changing the pattern on the SLM, you are able to choose the spatial frequencies that you'd like to collect, and the projections thereof you could reconstruct the signal from. Thank you. Thank you. I understand the problem.
If we have no more questions.
Sorry.
Yes,
Have-
Ma'am.
Well, is it possible to do this using a commercial projector?
You have to get the light collected from because the commercial projector is transmitting. So what was usually done, let me tell you a story, because SLMs are hard to procure back then. What the researchers from Instru did was to get an old projector, open it up, and get the SLM of the projector.
Yes.
Because a projector has an SLM or a DMT. Micro mirrors, digital micro mirrors. So they are both acting like spatial light modulators. So to do this without buying an SLM solo, if you have an old projector, you open it up and you get the SLM circuitry.
Okay. If we have extra projectors in the lab, maybe we can.
But another way of doing this is for you have to have some optics, some lenses, because what you need to do is project the Hadamard patterns on the wall, then project the reflected light from the object to that wall. And then what the single pixel detector will collect is the light from the Hadamard and the light projected from the object on the Hadamard pattern. Does that make sense?
Light projected from the Hadamard.
So if you have a projector, you project it on, reproject the Hadamard patterns on the wall, right?
On the wall, all right.
And if you have your scene, you project the scene on the Hadamard pattern. So actually, you can do this using two projectors. One, in place of having a physical object and a lens, and this lens and physical object is projecting the light from the object to the Hadamard, what you can do is you have two projectors, one projecting a Hadamard and one projecting your scene. You understand? And that's what you collect from the single one. That the combination of these two scenes would be what you will collect from your single pixel detector. Yes.
All right.
So because of course you can, because it's just the same. If you have an object and a lens and you illuminate your object, say you have a transparency, illuminate from behind, it's just the same as you have a projector projecting a scene on the wall. Nagets niyo ba, Mar? Again, two projectors projecting the two patterns at the same time. One Hadamard, one is the scene. Okay? And then you have a single pixel detector getting the light from both of the patterns projected on the same wall. Gets? Can you imagine? It can be done.
Yeah, but you only need two projectors. At least,
projectors,
yes,
yeah.
two.
So if you want to do experiments in the lab, just tell me and we will file permits for you. We'll do everything so you can do projects here in the lab. Okay.
More.
Right?
All right.
Where is Mar staying? Where is Alvin
Jensen.
staying?
Aldrin.
Jensen po, ma'am.
Yeah.
How about Aldrin?
Mama ko Fairview lang.
If you can convert your cell phones into a projector, we can lend you large lenses.
Yeah, Max
You
can
can
do that,
try.
ma'am. That's her.
Yeah, diba? So if hirap pang makapunta dito, we can actually do the experiment still at home. But you have to have two
smartphones, two lenses
yes.
as well.
Yeah. Lenses are easy to gambay. Okay.
If we actually still have more time for questions that can be addressed to both Aldrin and Mar. But if we have none, Ma'am Jing and Ma'am Ritz, do you have any announcements?
Of course, as what Dr. Loma said, let's support our TCCists and watch their so you have a feeling, guys, how a thesis is defended. Okay. Ritz, sorry, you have an announcement.
I don't know. Same announcement actually. Thesis defense.
Okay. So our big day for Max and K is on June 2.
Oh, May 31.
Hey, ma'am.
May 31, Ma'am Jing.
OMG, May 31. Sorry.
Tuesday next week. Yeah. Fake news.
No.
First day. Yes, ma'am. Actually,
Tuesday.
MS. Yeah.
Tuesday, 9:45 ba, Max? And 4 p.m. ba? Okay? First day. 4
Yes,
p.m.
ma'am.
gabi.
4 p.m. po.
So, but do please attend the rest of the the thesis support your batchmates kahit hindi sila tiga-instro, no? So give your support. Okay? Okay, so this is our last seminar. So I'm very grateful for you guys for lugging it through or chugging it and taking it like a champ. So, tara, last picture na natin for the seminar. Yes, Rene is here in the lab. He's downstairs. I'm very excited for you guys to join us here in the lab, especially yung mga graduating. Okay? So, di bale, sisikapin namin na makarating kayo dito. Okay? Kailangan lang ipaglaban. Okay ba? Okay, so picture na mga people. This is our last. So the next seminar would be next semester now, which is sometime in September. Okay. So, gonna get a picture here. Smile, everybody. Got you. Hindi ba dyan kuha din? Oh, si Rene may tour pop NIP. Sige. Habang marami pang time, tour ko naman kayo sa lab. Masanay na kayo. Yes, si Rene dyan sa baba, ako dito sa taas. This is, you can eat here, you can even sleep here. Okay? Okay? Come over to the other lab. You can use these tables outside. Okay. Where the rest of the team? Where's the rest of the room? So folks. Okay. Right. Marami tayong projector dito. Pwede yung paglaruan. Mga lumang projector. Pwede yung paglaruan. Of course, our very own NIP. Okay. So excited for you guys. Bali, malak na yan. Okay. Ang ating mezzanine, kung saan... Rene, nandiyan ka ba sa baba? Baka ikaw naman ang pwedeng mag-share. Rene.
Yes, ma'am.
Sige.
Maraming pagkain dito. Ginaubusan. And may mga drawer tayo for your for food. Stress foods. O, di ba? Kasi ang number one rule dito, sabi nga ni Ma'am Jing, bawal magutom. Kasi meron din tayong bed, guys. Bibili si Jem ng bed. The foldable bed natin.
Ay, may amag na yan.
Everybody say, thank you, Jem, kasi papalitan niya ang bed.
May amag na yan. Chinek ko last week.
Yung foam lang
Kung
kailangan
nainitan-
palitan.
True.
Foam lang.
Kasi aircon talaga pinunta ko dito, guys. So, papainggitin ko kayo. Yung 17 degrees. Yun lang.
Magdala kayo ng ng sweater pag nasa lab.
3 layer.
O dito naman, sa refrigerator, lalagyan na ng food. Sabi sa inyo bawal magutom. Ayun pa, microwave oven, coffee maker ba kamo, or hot water, o dispenser. Saan na yung tubig dyan? Ay, order pa. Patis. Gusto niyang patis, honey, patis.
True.
Sige, looking forward, guys. Ibale, hopefully, kung normal na sa mall, dapat kaya rin natin bumalik sa normal dito sa lab. Okay?
Ma'am Jing? Yes, may optical table na po ba na pwedeng gamitin or ginagamit pa rin lahat ng optical?
Ginagamit pa, pero kung sabihin mo na kailangan mo, we will set it aside. Kasi may rights ka naman doon, optical table mo yan eh. So,
Right.
yes. So,
Si Rain and si wala dito si Tating. Baka gusto lang mag-experiment sa mid-year.
sige, go.
Yeah.
So, looking forward to everybody. Excited na kaming makapiling kayo at kayo
Ayun
ay
si Tati.
magagamit ng
Yeah.
laboratory. Okay?
Mm-mm.
Okay. Ingat guys. That's it. This is for this sem. Bye-bye.
Good luck sa thesis.
Yes, good luck,
Woo!
Kay.
Congratulating.
Good luck.
Okay,
Bye.
fighting.
Thank you po.
See
Galingan
you
nyo.
soon.
See
MS,
you.
MS naman.
MS na.
Yeah.
Good
Let's see
luck
Max.
po.
Go Max, go Max.
Okay, okay.
Hi guys.
Bye guys.
Bye po, ingat
Ingat.
po.
Po.
Oh.
See you soon.